Okay, welcome back everybody. Project 4, here we go. Number 1, the birthday paradox. Suppose you're in a room with 24 people. What are the chances that at least 2 people in the room have the same birthday? Well, we've taken a look at this in class before, and we know how to use Wolfram Alpha to calculate this, and we also know how to calculate it using the laws of probability, but we're going to run what's called a simulation. So now that we know something about probability, what's your educated guess? And we know that it's actually higher than one would expect. The probability is actually difficult to calculate mathematically, however, it's ideal for simulation. So to run this simulation, let's begin with the following information. There's 365 days in a year. We'll ignore leap years. There's 25 people in the room, you and 24 others. Each person could have any day of the year as his or her birthday, so each birthday is equally likely. So we'll start your simulation with one room of 25 people. Use Megastat number generator or go to this website to generate 25 random integers from 1 to 365 and display them in column 1. Okay, so I'm going to just go ahead and use Megastat. So hopefully you can see what I'm doing here. So I'm going to go add-ins, Megastat. I'm going to go down to generate random numbers. And actually it wants an open workbook. So I'll open a new workbook. Okay, Megastat, generate random numbers. And we're going to generate 25 numbers. You have to click fixed values. We want these to be fixed values. Right click here, decimal place is 0, because it's not like we're having 365.82 or something like that. So no decimal places. Make sure that says 0 there. We'll go ahead. Minimum is 1. Maximum 365. Go ahead and hit OK. And we have randomly generated now 25 numbers. What I'm going to do is just copy paste. So just a little tricky here. I'm going to hit copy and then I'm going to go to sheet 1, but I'm going to right click and I'm going to hit paste special. Make sure you paste those as values, okay? And hit OK. Okay, good. Now what we want to do is we want to know if there's any matches in there. Does anybody have the same birthday? Well, clearly, we could sort through it with just our eyeball, but that might make one dizzy. So let's use a function over here. COUNTIF is a command. So you see I'm going up here into the function window, and I had actually, let me show you where I did that. I went up here and I hit f of x for function, and COUNTIF, if you don't have it, I have used it recently. If you don't have it, you can type it in here. COUNTIF, hit OK. And it asks you range. And your range is going to be the whole range of values that we have here. So I'll highlight that. And your criteria is if basically what that translates to is if any of those values is equal to the slot in A1 will have a match. The cell A1 will have a match. That's the way that translates. So it scans through that range of values to see if any of them match A1 is what it does. And we'll hit OK. Okay, now what we're going to do is click and drag all the way down. Now you'll see that in this column is all ones. That means that each one of those observations is unique. If there would have been a match, you would have seen a 2. Or perhaps a 3, if there were multiple matches. So all being ones, it means that each one of these is unique. Let's try it again. So in this situation, there were no matches. Okay, so let's see if I can zoom in here. it says if the same number appears more than once, then you have people with the same birthday. And it says, please attach one page of your spreadsheet. So we're going to copy paste that column. Well, we had done that already. You can actually copy paste this, or you can print out your whole worksheet when we're all done. Let's see what the next part of the lab says. Okay, so we just did the experiment. We just ran it once, so clearly you have to do repetition. So, did you find at least 2 people with the same birthday? So in my situation, it was a no. In your situation, it might be a yes. It says, in order to calculate the probability of finding at least 2 people with the same birthday, we must repeat the experiment many times. So now we have to let's simulate 25 rooms, each with 25 people. And, use Megastat or this website that I gave you to generate these random integers. So we have to do this again. So if you think about it, 25 rooms filled with 25 people, and in the end you're going to have 625 random numbers in these various columns, in these 25 columns. And the end game is, of the 25 columns of numbers that were generated, how many of them had at least one matching pair? Well, let me just give you a little idea here of what would happen if there was a match. Since my first one I didn't get a match. Let me just give you an idea. Suppose, I'm going to copy paste this into a new column. Okay? Now I'm just going to make this up. Suppose there was another number here, 258. Okay? And suppose I went over here and I did the COUNTIF function again. So you can see what it would look like. Range. Again, I would highlight the range of values that I'm interested in scanning through. And then the criteria is, do any of those numbers match what's in C1? And it says yes. Notice here there's a 2. Okay, then, just to show you what that would look like, if I click and drag this all the way down, notice that every single thing, and I'll highlight it on here for you as well, notice that there's all ones except here there's a 2. And what that's basically saying is there's 2 observations of the number 258. Okay? And you can see that happening right there. And just to give you another idea, I did it again. I copy-paste the same numbers, but I just tweaked it a little bit so you could see what would happen. So I have a repetition of 258, and it appears there. So, you see the number 2. But I also, what would happen if here's 111 and here's 111, and you see the number 2. So basically that means that 111 appears twice in the list, and 258 appears twice in this. It'll list it, at the first observance. Okay? That'll help you just scan through your data quickly to know if there is a match or not. So now let me actually show you how to keep continuously generating those random numbers in an easy way. I'm not going to do all 25 columns for you, I'm just showing you the procedure. Okay, so if we want to repeat this procedure 25 times and generate 25 rooms of 25 people, you can go to Megastat, go down to generate random numbers again, but this time keep it on live functions. See how I have it clicked on live functions? So I'm going to do 25 values, live functions. Make sure the decimal place is set here at 0. Okay, minimum 1, maximum 365. And then I'm going to hit OK. And see how it says press F9 to recalculate the values? So what's neat, watch what, I'm going to hit F9 on the keyboard, okay? F9, F9, F9. See, my numbers are changing. You see those numbers changing? Every time. So what's happening is each time I do that, so I'm going to grab this column here, right? Copy it, but remember, when you go to paste it in, go to Paste Special. Paste Special as values. You have to paste it in as a value, though. So it's like static. Okay, so we can, and again, we could scan through there with our eye, but it's safer to use the command. So over here, I'm just going to practice doing that with you one more time. count if. Okay, your range, highlight the range. And your criteria is that if any of those values equals the first guy. And hit OK. Now that's neat because right away we see there's a match. So that would mean your second classroom there was a match. And that means somebody in here had birthday 337. And if you scan through, what's neat about that is if you scan through, you can actually see it. There's a 337 and there's a 337. Oops. Sorry, I kind of erased that there. There we go, 337. So, but as soon as you see that all of these are ones, but there's a number 2, that triggers you that there was a match. So what you would do is you would continue that 25 times. So you'd have 25, repetitions of the experiment. And basically, in the end, did you get 13 out of 25? Did you get 14 out of 25? Did you get 8 out of 25? What was your theoretical probability? Your experimental probability based off of this experiment that we're running. And it should be arbitrarily close to the mathematical probability that you would compute using Wolfram Alpha, which we're going to look at in a moment. Okay, so the next part here says, part D, says, based on your simulation, what is the probability that in a room of 25 people, at least 2 people have the same birthday? And it says find the theoretical probability using Wolfram Alpha. So based on your simulation, now I'm just say you did the 25 rooms and say 12 out of 25 had. So 12 out of 25 might be, for example, your experimental probability. Okay. Then we want to compare that to the theoretical probability. And we did that in class, but I'll remind you how to do that using Wolfram Alpha. Okay, so I'll go back a step here before I did that. So I just went to wolframalpha.com, and you see the search window here. And I just typed in birthday. This is a well-known problem, so I just typed in birthday paradox. Hit enter. And it even tells you, assuming birthday problem with leap years. Number of people, 23. Now they're using with leap years here. Now let's make the room 25 people. Now you see, once you have, it's thinking. You can change the number. See that at least you're looking at about a 57% chance. Okay? And once you have, what's interesting is once you have about 50 people in the room, and I'm changing that to 50. Now you see down here the probability is 90, and I'll highlight it on here for you. Now you see that the probability jumped up to a 97% chance. Once you've got 50 people in the room, 97% chance someone shares your birthday. That's why they call it the paradox, because it goes against your instinct. Okay? But you saw with 25 people in the room what the theoretical probability was. So when you do your experimental probability, it should be arbitrarily close to that. Okay? In other words, a simulation should end up close to the theoretical probability. Okay, let's see what's next. Okay, actually I just wanted to reiterate, just so you know what that means here. In part E, it says, use Wolfram Alpha to find this theoretical probability, and it says compare your empirical probability to the theoretical probability. Are they close? And that's exactly what I meant. The empirical probability is what you got from your repeated experimentation, and the theoretical probability is what you got from Wolfram Alpha, or from crunching out the formula like we did in class. Okay? Number 2, it has been reported that we're going to head on to the binomial distribution. 39% of college students graduate in 4 years. Consider a random sample of 30 students. Let the random variable x be the number of students who graduated in 4 years. Use the probability function of megastat to answer the following. Okay, so we're going to copy paste the distribution into Word. And by the way, anything for this project, like your spreadsheet on the birthday problem, make sure you attach all that documentation. So your birthday spreadsheet, attach all that. Okay. Part B, find the probability that at least 13 students in a sample of 30 will graduate in 4 years. So I want to show you how nice megastat makes, I'm actually going to pull up a new sheet, makes doing this. How easy. We will go to probability. We'll go down to discrete distributions. Okay. Up here, it gives you the choices. This is a binomial experiment. Okay. Let's see if I can actually shrink that right beside it so I can keep my eye on it. 39% is your probability of success, and your n is 30. I'm just going to fill that in here. N is 30. Probability of success is 39%, or probability of occurrence. And just hit OK. Ignore the error message. And let me page down on the worksheet here. And see, like I said, when it said copy-paste the distribution, you can highlight, and you can and it's neat. It tells you the expected value and the standard deviation of the distribution as well. So you can highlight that whole thing and copy-paste that into Word. But let's take a look at the question again. So the question was, find the probability that 13 students in this sample of in a sample of 30 will graduate in 4 years. So what's nice, let me show you how to read this distribution. What's nice about the distribution is once you have it, you can literally read it from the table. So here, x equals 13. Ignore the cumulative probabilities for now. Okay, P of x is what we're interested in, P of x. So the chance that 13, let's see if I can highlight this here, will graduate in 4 years is 0.129. Okay? 65. So about really close to about a 13% chance of that happening. So again, to answer, let me pull this back up. To answer this question, all I was doing was reading from the table. Okay, and I got about a 13% chance of that happening. Now, let's try the next one, and really it's just going to be about reading these tables. Find the probability that 15 or fewer in the sample graduate in 4 years. Now, here's where I will show you how to use the cumulative probabilities in a nice way. 15 or fewer, let's think about this logically. 15 or fewer, I'd have to take all these decimals here and add them all up. But what's nice is the cumulative probabilities is already added up for me. So the 0.9216 represents the probability that x is less than or equal to 15. So for the 15 or fewer, the 0.9216. So what I'm getting at is sometimes it's a lot easier, note to self, to use the cumulative probability. Okay? This one right here. Otherwise, you'd have to add all these decimals up, which would be kind of a pain, right? And I'm just going to re-highlight that. You'd have to add up all the decimals that correspond, 1 through 15. Okay? Oops, let me erase that. Got a little too thick there. All right, so again, just try to utilize the cumulative probabilities to help you so you don't have to be adding so much. Okay? Now in Part D, it says, find the probability that more than 15 students in the sample graduate in 4 years. So again, let's talk about, how we can kind of be slick. In Part D, just map this out, the probability that more than 15, that's how you translate that mathematically. So more than 15 means 16 or 17 or 18 or ... all the way on up. So I'd have to take 16, and add the corresponding decimals all the way on up. The 0.04 plus the 0.02 plus the 0.01. Or what I could do, the opposite of 16, 17, 18, and on up, we had calculated, so really I could use the complement rule, and I could take 1 minus what we got from Part C. So, I could take 1 minus the 0.92116. Okay, so just again, utilizing the cumulative probabilities in the best way possible. All right, let's try again. So my goal isn't to walk you through this completely. So number 3, I just want to give you a push. So in number 3, it says it was reported that 9% of automobile accidents in PA are alcohol related. Suppose we take a random sample of 100 accidents and let the random variable x be the number of automobile accidents that were alcohol related. It says copy paste the probability distribution and then find the probability that fewer than 35 accidents were alcohol related. So we're going to do the same situation. Your p is 9%. It's a binomial, so your p is 9%. Your n, your sample size, is 100. So let's try that again. We'll go megastat, probability, discrete. Your sample size is 100. And your p was, we already forgot what we said it was, 9%. Okay, and hit OK. Ignore the error message. And again, it spits out the distribution for us. And what's nice is if you look down, oops, actually it's hidden under it's hidden under this graph, which we're going to need later. But so what's nice is it reminds you what distribution you're dealing with right here. Notice it reminds you used n is 100 and p is 0.09, and it gives you the corresponding distribution. So it's going to ask you various questions. So just to give you a push, find the probability that fewer than 35 accidents were alcohol related. Now all we have to do is read the table. So fewer than 35 translates to 34 and below. Now we got to be a little slick though. And here's what I mean by that. Fewer than 35, that's 34 and below. Even if I use the cumulative probability, it looks like it's 100%, right? But actually, if you put your cursor over it, it's just due to round-off error. It's not perfectly 100%. If you put your cursor over it up here in the function window in Excel, you're actually going to see its point, and I'll highlight that. You're actually going to see it's 0.9999999 and eventually a 28 way out at the end. So, all these things that look like they're 100% cumulative probabilities is really just very, very close to 1, okay? So let's see what the next one asks. Then it says, find the probability that between 40 and 60 inclusive were alcohol related. Actually, I just realized something. Ooh, it's good I went through this. I just realized there was a typo in your write-up here. That should have been between 4 and 6, not 40 and 60. Okay? Find the probability that between 4 and 6 inclusive were alcohol related. So let me go back to the table. So between 4 and 6 inclusive, that basically means that we're going to have to take this decimal, and this decimal, and add it together. So basically the 0.03, the 0.057, and the 0.089, and add that together right here. Okay? And likewise, there was a typo. I'm so glad I caught that. And last one, it should say find the probability that at least 5 were alcohol related. So remember that at least 5 translates to 5 or more. So just to give you a hint, 5 or more, you could add all of these decimals together, or instead of doing that, you could use the complement rule, hint, hint, hint. So, but you'd have to take 1 minus the opposite of 5 or more, so you'd have to take 1 minus this decimal right here, the 0.04739. Okay. So I kind of gave everything away for that, but I'll send out a revised version that didn't have those typos in the document. Okay, now the way I'm going to work this for time's sake is if I do number 4 with you, you'll inherently be able to do number 5, okay? So number 4, it says the shape of a graph of a binomial distribution depends on the value of both n and p. To see how the shape changes for a fixed value of n, you will let p vary from small to large and graph each probability distribution. So, let's first P is 0.18, then P is 0.47, then P is 0.88, but we have a fixed value of n, say 10. And describe what happens to the shape of the distribution for small values of P, and then for large values of P, and then then we'll look at the last one together. So let's just go ahead and start that. Let's use a P of 0.18 and an N of 10. And all of these things you would copy into your Word document. So addends, megastat, probability, discrete. N, you're going to fix at 10, and we're going to start off with you can write 0.18 or you can write 18%. Hit OK. Just hit OK. And it's the graph that we're interested in, so let me page down. See, this worksheet will keep, it'll keep compiling everything that you've done so far, so sometimes I scoot it off to the side. So here is the first graph that we would need to copy-paste. Now notice, for the n equals 10 and a small p, we have what? Right skew. Tail is to the right. Okay? Now let's see what happens. So now let's do it again. Probability, continuous. Oops. I didn't mean continuous, I meant discrete. Probability, discrete. Now let's change that to, what did we say the higher one was? I want to do the higher one, 0.88. So let's change this to 0.88. Hit OK. Make sure you page down and retrieve the correct. See, I like to scoot it over to the right. Oops. Scoot over to the right a little bit. Now you'll see quite the opposite situation. So now for the same value of n, but a high p, now we have skewed left. And you could imagine, if you keep the p, probability of occurrence somewhere in the middle, around 0.5, perhaps there's symmetry. So let's try that. Addends, megastat, probability, discrete. Now let's keep that at about, I forget what it said on your paper, something close to 0.47. Hit OK. And again, I page down to try and find that. There it is. See? So when we keep the same value of n, but our probability of occurrence is near 50%, we're seeing more symmetric distribution. And that's what we were getting at in terms of the write-up. So that ought to help you a lot with number 4. So, big hint. So in D, when it says symmetric binomial distributions seem to have a value of p near what value? Well, p was near 0.5 when we saw symmetry. And, for large values of p, we saw what kind of skew, is what I'm looking for here. And for small values of p, we saw what kind of skew. So we pretty much tackled that together. And then in number 5, you're going to do a similar experiment, except this time you're going to fix p and you're going to let n fluctuate. Okay? So I am going to jump down to number 6 with you. So we're still running, in number 6, we're still running a binomial experiment. I always say if you can map out your n's, your p's, and your q's, if you've got a fixed number of trials and a probability of success and a probability of failure and all trials are independent, it's starting to look like a binomial experiment. So it says Singulair is a medication whose purpose is to control asthma attacks. In clinical trials, 18.4% of patients in the study experience headaches as a side effect. Would it be unusual to observe 86 patients who experience headaches in a random sample of 400 who use this medication? Okay, so we know that the random sample is 400. The probability of occurrence is 0.184. Let's go for it. So addends, megastat, probability, discrete. Sample size is 400. Probability of occurrence, we said, was was it 0.147? Let me double check. Oops, sorry, 0.184. My head is en la luna, I suppose. Okay, and then hit OK. And then again, we're reading from the table. So here, I'll just highlight this. I always make sure I grab the right table. So here it tells me my distribution, my binomial distribution when n is 400 and p is 0.184. Now I'm going to read. So I'm going to page all the way down that table till I see, the probability that 86 people get that side effect. Page all the way down. You see, okay, the probability that 86 people get the side effect is pretty small. So the probability that x is equal to 86, I'm going to write this mathematically, is 0.01419. So would it be unusual? Yes. So remember, unusual to our author is less than 5% chance. Okay, let's try the next one. Ah, good news. You made it to the finish line. Turns out number 7 is the last one, and it's a Poisson random variable. So, and again, Megastat makes that real nice and easy for us. It says, recent crime reports indicate that 3.1 motor vehicle thefts occur each minute in the U.S. Assume the distribution of thefts can be approximated by a Poisson probability distribution. Obtain the probability distribution and copy it into your document. Calculate the probability that exactly 4 thefts occur in a minute, that there's no thefts in a minute, and then what's the probability that there's at least 1 theft in a minute. Well, you can imagine, and you probably saw it, it's the same place where we were before. You just have to highlight Poisson. So, Megastat, probability, discrete, and you probably saw it over here. Highlight that. Mean rate of occurrence. So you're probably wondering what to put in for mu, mean rate of occurrence. Well, remember, now's a good time to talk about this. Remember that mu is equal to lambda t on the Poisson random variable. So it said that 3.1 per minute. Let me look back at the Word document here. So notice that it said 3.1 motor vehicle thefts occur each minute. But then it's saying, what's the probability that 4 thefts occur in a minute? So the time interval is still a minute. So, long story short, I'll write it right on here. If mu equals lambda t, and lambda is this rate of occurrence, which is 3.1 per 1 minute, but time is the time interval over which you're looking, which is a 1 minute interval. Well, what happens is the 1 minutes cancel out, and mu basically equals 3.1. So a lot of people, you may have guessed that. A lot of people say, should I just put 3.1 in there? Yeah, but that only happened because the 1 minutes canceled out. So 3.1, we'll put that in. We'll hit OK. Just ignore that error message. And I'll page down. And I have to move this over. I don't know why it layers things like that, but yeah. So what's nice about the Poisson distribution is it reminds you of what you input, okay? And by the way, you want to highlight, when you're copying this into your document, just highlight all of this. Even that. You can place all of that in there, okay? So, just to give you a little push, when it said the probability that, 4 thefts would occur, you can read that right off of your chart. 17% chance. So the probability that x equals 4 is equal to 0.17. Okay, hope that helps. Good luck, everyone.